Thank you very much, and thank you for giving me the opportunity to speak here, and thank you to all of you for listening. So the Erdős-Ginzburg-Sieve problem is a classical problem, classical extreme problem in discrete geometry, and it asks the following question. So for given positive integers m and n, we are wondering about the following question: what is the minimum integer s such that among any s points in the n-dimensional integer lattice z to the n, we can always find m points whose centroid is also a lattice point in z to the n. So recall that the centroid of a collection of m points, p1 to pm, is simply the average. So simply the average as vectors in Zn. Now the average is not necessarily in Zn, like the average, the average, yeah, that's what I wanted. Yeah, so the average may have rational coordinates, but so we are looking for m points so that this average, the centroid, still has integer coordinates. And it's not hard to see that that means that we want the sum, so the sum of the m points. This clicker does not behave the way I... Okay, so the sum here, P1 plus Pm, that you want all coordinates of that sum to be divisible by m, because that's exactly the same as saying that this average here has integer coordinates. Okay, so we are looking for the minimum possible number s, so that it's the case that whenever we pick s points in the n-dimensional lattice z to the n, we can find m points so that their sum has all coordinates divisible by m. To make that, maybe it's still a bit abstract, especially since I'm so bad with this pointer, so let's make a more concrete example. So in my example, so here's again the same question, but so now as an example, let's consider n equals 2, because then the lattice is two-dimensional, that fits best on the slide, and let's take m to be 3. Then the picture doesn't get too big. So here we are given some 4 points. And so we are now trying to find 3 points whose centroid is again a grid point. So in this case, that's possible. You can take these 3 red points, and then you see their centroid is that point marked with a cross, which is again a grid point. So for those 4 points, it is possible to choose m equals 3 points whose centroid is again a grid point. However, that is not always possible with 4 points. So here we see 4 points for which we cannot choose 3 whose centroid is again a grid point. So that means 4 is not enough. We need more. In fact, you can see that even 8 is not enough. So here there are 8 points, and you can see that even there you cannot choose 3 points whose centroid is again a grid point. And so it turns out that the answer for n equals 2 and m equals 3 is that one needs 9 points. So this example shows that 8 is not enough, and you can prove, or believe me, that 9 points are enough. So that means for n equals 2 and m equals 3, the answer to that question is 9, but we don't necessarily just care about the specific example n equals 2 and m equals 3. That was just to illustrate the problem. Okay, so here's again the problem. And so the answer to this question is called the Erdős-Ginzburg-Sieve constant, and it's denoted like this. Okay, it's denoted by this. This pointer still doesn't work. So it's denoted by this s of zm to the n. And so why that strange notation? Well, this notation reflects that this problem can be translated into a problem about sequences in z modulo m to the n, because in fact, as we saw before, what really only matters here are the remainders modulo m of the coordinates of the points, right? Because we're looking for m points whose sum has all coordinates divisible by m. So in the end, basically all that matters is the remainders, and so we can translate that naturally sort of in z modulo m to the n. That's where this notation comes from. So Erdős-Ginzburg-Sieve constants have been studied intensively, but despite of a lot of attention for many decades, there are only very few known exact values. So here is, as far as I know, essentially a complete list of all infinite families of known values. There are a few more specific known values for specific pairs of small numbers n and m. And so these are the infinite families of known values. So as you can see in this list, it's known if the dimension n is 1, if the dimension n is 2, So then we know it exactly as given in the first 2 bullet points here. If n is 3 and m is of a rather specific form, having only certain small prime factors, then this answer is known as in the 3rd bullet point. If n is 4 and m is a power of 3, the answer is known. And if m is a power of 2. So the first 4 points are for small dimension. The last point is if this number m of points we're looking for is of the very specific form to be a power of 2, then the answer is known. And so as you can see, mostly the answer is unknown. Yeah. So since it seems to be very difficult to determine this quantity exactly, one goal might be to try to understand how this behaves as a function of m and n. So for extremal problems, that's sort of often the case. If it's just completely out of reach to try to nail it down exactly, we first try to understand the growth behavior of the answer. And so for fixed dimension n, the growth behavior is relatively well understood. So if you fix the dimension n, then this function is a linear function of m. We've seen that on the previous slide for these examples for small dimension n. Maybe you remember there was for n equals 1, this was 2m minus 1. For n equals 2, it was 4m minus 3. So of course, 4m minus 3 is not strictly speaking a linear function, but it grows linearly, meaning that it's upper and lower bounded by a linear function of m. Okay, so Allon and Dubiner showed this in general, that for any fixed dimension n, this quantity can be upper and lower bounded by linear functions of m. That it can be lower bounded by linear function of m is trivial because m is a trivial lower bound. So what they showed, Allon and Dubiner, is this upper bound written there. And so if you fix n, then this first factor becomes sort of fixed, and so it's a linear function in m. Okay, and so this bound was relatively recently improved by Zakharov, who improved the bound to, I'll stop trying to point at this, but yeah, here. Okay, so he improved this bound to this in the case that m is a prime which is sufficiently large with respect to n. So basically he improved the linearity factor in this bound. Okay, but in the opposite regime, the answer is completely open. So the question that's completely open here is, or one question that's completely open here is, here we understand it relatively well if we fix the dimension n and look at it as a function of m, but if we do the opposite, we fix m and look at this as a function of n, then the growth behavior is still an open problem. And so, in this talk, I want to tell you a little bit about what's known in the different ranges for this problem, what techniques are used, and in the end, I'll talk more about this open problem and how much is known about it. Okay, so in all these different results I told you about, the first step is to reduce to the case where m equals pre is a prime. So here's again the definition of this S of z modulo m to the n. And so there's a relatively easy lemma giving an upper bound for this quantity, this Erdős-Ginzburg Ziff constant, if this number m is composite, so if it's a product of k and l, then we get an upper bound for this quantity in terms of the corresponding quantities for the factors k and l of m. So here is this inequality. So if we take m to be kl, we get this upper bound in terms of the Erdős-Ginzburg Ziff constant with k and l in the bottom. And so, as you can maybe imagine, this lemma gives you an upper bound if you have a composite m in terms of the factors. And so it's maybe not hard to believe that this lemma can be used to reduce upper bounds to the case where m is a prime. And so that was indeed used for all the previous results I told you about. So in other words, for all these previous upper bounds I told you about, it suffices to study the case where this m is a prime, and then instead of s of z modulo p to the n, I write s of fp to the n. Okay, so because every talk should have a proof, I'll also give you the proof of this lemma. So that's a bit more satisfactory to believe that we can reduce to the case of a prime. Okay, so here's a proof of this lemma. So now so remember that n is the dimension and m is k times l. So m is k times l, so we are trying to find kl points among a given set of points whose centroid is again a lattice point. Okay, so we want to show this upper bound here. We We want to show this upper bound here for this quantity, so that means we need to show that that many points as on this right-hand side of the inequality are enough in order to ensure that we can find KL points whose centroid is lattice point. So let's consider any set S of that many points in Z to the n, and our goal is to find KL points whose centroid is again a lattice point in Z to the n. So we do this in step. First, let us find L points in the set S whose centroid is again a lattice point. So we can do that because this quantity here is at least this. This quantity is at least S of Z L to the n, so we can definitely find L points whose centroid is again a lattice point. So now let's delete these L points. So let's put them to the side. Let's delete them. Now we have some points left. Still quite a lot, and repeat the process. So we again find L points whose centroid is a lattice point in what we have left. We put those aside, and we repeat. So how many times can we do this? Well, after having done this, S of Z modulo K to the n minus 1 times, so having done this so many times, and having removed so many groups of L points, we still have S of Z modulo L to the n points left. So we can still do it another time. So that means in total we can do it S of Z modulo K to the n times. So we have found S of Z modulo K to the n groups of L points, and each of these groups has a centroid in Z to the n. So now, now let's look at all those centroid points for all these groups. So these are now grid points in Z to the n, and among these S of Z modulo K to the n centroid grid points, we can definitely find, by definition of this quantity S of Z modulo K to the n, we can find K points, so K of those group centroids, so that the centroid of those centroids is again a lattice point in Z to the n. But so that now means if we take those corresponding groups, we have now found K groups of size L, so that makes together K times L points, and all together the centroid is the centroid of those centroid group points, and that's a grid point in Z to the n. So that shows this inequality. And so now hopefully you'll believe me that you can use that basically to reduce the upper bounding to the case of a prime. And so for the rest of the talk, we'll only worry about the case where M is a prime. Okay, so let me say a little bit about the different proof techniques that were used to obtain these results that I told you about for different cases for the dimension. So, as we already said, these, we can always, for upper bounding, reduce to the case where M equals P is a prime. And so the first bound that I told you about was the case where the dimension is 1. And so that result is actually due to Erdős, Ginzburg, and Ziff, giving rise to the name Erdős, Ginzburg, Ziff constant. So they showed that for dimension n equals 1 in this notation, which wasn't quite the notation they used at the time, we have that this S of Fp to the n, so then S of Fp to the 1 is 2p minus 1. And so this can be proved as an easy application of the combinatorial Nullstellensatz, which is due to Allon in 1999, although, as you can see in the years here, the original proof of Erdős, Ginzburg, and Ziff was different. But sort of with a modern technology, with the combinatorial Nullstellensatz, this theorem basically becomes an easy exercise. So when teaching the combinatorial Nullstellensatz in a class, one can basically give that as an exercise on the homework. The case of dimension 2 is already much harder. So for dimension 2, the answer is, as we already saw earlier, S of Fp squared is 4p minus 3. And so this can also be proved with the combinatorial Nullstellensatz, or alternatively with the Chevalier-Warning theorem, which is sort of similar. But the proof is much more involved. So it's not just an easy exercise anymore. And so for those of you not familiar with these combinatorial Nullstellensatz techniques, so these are basically polynomial techniques. So these are polynomial techniques in combinatorics. So it's some theorem saying something like if you have a polynomial with certain properties, then you find a non-zero point, yeah?
So I guess because you're reducing this to F1p, that's a multi-set, not just a set. Your big points, I guess.
Yes.
F1p has p points in it, so choose 2p minus 1. You have to.
Yeah. So it's a problem. Yes. So it's a problem about multisets or sequences. I mean, typically it's phrased in terms of sequences. Yeah. But I mean, so far I think I defined. So So I defined S of Z modulo M to the N as the notation for the answer for the problem. So I never really translated the problem, but you're absolutely right. If one does the translation, it's about sequences or multisets. So far, we've sort of talked about the geometric problem, but I had to have a notation. I wanted to stick to the standard notation for that. Yeah. Okay, so yeah, maybe I should add to the answer. So if you're in the geometric setting with grid points, it doesn't matter whether you repeat them or not, because
I understand.
Yeah.
Bring over a finite field, you know, and linear algebra finite field, and things like that, it doesn't matter.
Yes, yeah, but you have to, yes. If you translate to that setting, you have to take repetitions. But okay, so here's the result that I mentioned of Alon and Dubiner for fixed dimension n. So they showed that for any fixed dimension n, this function s of fp to the n grows linearly with p. And so their proof is by induction on the dimension n. And the induction step relies on results from additive combinatorics as well as arguments using spectral graph theory, so studying eigenvalues of certain adjacency matrices of certain graphs. And so, as you can see, that's again an algebraic technique, but it's very different from the algebraic technique used for dimension n equals 1 and n equals 2. So in the case of dimension 1 or 2 is this combinatorial no-Stellensatz techniques, which is sort of basically using certain polynomial techniques. And this is a rather different algebraic technique they used to get their bound for fixed dimension n. Okay, but neither of these approaches seems to work for large dimension n. So as I said earlier, it's still not understood how this function behaves if you fix the prime p and let n be large. So the open problem is how large is this for fixed prime p at least 3 and large dimension n. Okay, and so that's what I want to talk about for the rest of this talk. So let's now, from now on, assume that p at least 3 is a fixed prime. The case p equals 2 is boring, because then the answer is known and it's very easy. So let's assume that p at least 3 is a fixed prime and n is much larger than p. And so here again is the definition of this Erdős-Ginzburg constant. So again, the definition is in this purely geometric setting. But yes, as I guess we discussed with respect to this question, one can translate it into a problem about sequences in fp to the n. And so, as we also already saw, for p points in z to the n, the centroid is a lattice point. And so basically, this is roughly getting at how to translate it. So for p points in z to the n, the centroid is a lattice point in z to the n precisely when the sum of the p points has all coordinates divisible by p. And so that means we can now, as we already said before, translate this into a problem in z mod p to the n, or in other words, in fp to the n, by basically just considering the remainders of the coordinates of the points modulo p. So that means we consider the points as possibly repeated, so that exactly gets at your question, possibly repeated elements, possibly repeated elements of fp to the n. And so now we are trying to find p of those elements, of those possibly repeated elements of this multiset or sequence of elements, whose sum is the 0 vector in fp to the n. So that means we arrived at the following equivalent definition, which is, I think, where your question was getting at, the following equivalent definition for S of fp to the n. So S of fp to the n is the minimum integer S, so that among any sequence of S elements in fp to the n, there is a subsequence of length p whose elements sum to 0. Okay, so I mean, that's basically just dry juggling around of the definition. Okay, so equivalently, you can again rewrite this S of fp to the n minus 1, so just subtracting 1, you arrive at the following equivalent problem, namely S of fp to the n minus 1 is the answer to the following problem. What is the maximum possible length of the sequence of elements of fp to the n without a subsequence of length p summing to 0? So here you ask sort of what's the minimum S, so that it's always long enough to find the length p subsequence summing to 0. That's sort of equivalent to asking, like, what's the longest subsequence that you can't find this? Up to 1, that's the same question. Okay, so now suppose you have such a sequence of elements of fp to the n without a subsequence of length p summing to 0, then obviously every vector in fp to the n can occur at most p minus 1 times in the sequence, because if a specific vector appeared p times, those p copies of that vector would form a subsequence of length p summing to 0. And so that means every vector occurs at most p minus 1 times. And so that means up to a factor of p minus 1, this problem is now equivalent to the same problem if we don't allow repetitions. So sort of allowing repetitions or not in the sequence only makes, changes the answer to a factor of at most p minus 1. And since we are now in the case that p is fixed and n is large, this factor p would be a constant factor. So that means up to a factor which is constant if we fix p, this problem is equivalent to asking what is the maximum size of a subset of fp to the n, so now not a multiset, so no repetitions, without p distinct elements summing to 0. So that means if we can answer this problem, then we will have essentially answered this problem, at least in the range where p is fixed and n is large. Okay, so that means for the rest of the talk, we can now focus on this problem, which is maybe a little bit easier because it's about sets and not multisets. So let's again p at least 3 be a fixed prime and n large. And the question is, what is the maximum size of a subset of fp to the n without p distinct elements summing to 0? So within fp to the n, so for those of you who sort of fell asleep, you can come back in. It's a new question that's self-contained. So you have fp to the n. You're asking how large of a subset can you take of fp to the n so that in your subset you don't have p distinct elements summing to 0. So how many vectors can you pick if you're not allowed to pick p distinct vectors with sum 0? Yes?
For lower bounds for these kinds of problems, are there constructive constructions or are they existential?
So let me get back to your question when I actually talk about the lower bounds. Is that okay? Yeah, okay, so we have seen that the answer to this Erdős-Ginzburg problem in the range of p fixed and large n agrees with the answer to this problem up to a constant factor. And so let's focus on this problem now. And so now let's talk about first a very easy lower bound, and then I come back to your question. So just a very easy lower bound to illustrate the problem maybe is a lower bound of 2 to the n, so that you can get by taking 0, 1 to the n, so that means all vectors in fp to the n whose coordinates are all either 0 or 1. So then you can check that if you only take the 0, 1 vectors, then you won't be able to find p distinct vectors whose sum is the 0 vector, and so therefore that's an allowed set, and so that means 2 to the n is a lower bound for this problem. So now we might wonder how, well, that's sort of pretty trivial, but must be able to do much better. In fact, the best known lower bounds are only a little bit better in some sense. So the best known lower bound for p at least 5 is roughly 2.1398 to the n, and the best known lower bound for p equals 3 is 2.2202 to the n. And so now coming back to your question, so the lower bound so this lower bound is obviously, the one 2 to the n is obviously constructive. I even wrote down the construction. The lower bound for p at least 5 is also constructive. So it works by taking 96 particular vectors in z to the 6, and then taking a product of that. So this 2.1398 is the 6th root of 96. And if that's not true, then I misremembered the numbers, but sort of there was a specific number of vectors in z to the 6. So that's also completely constructive if you can write down this list. And so then this lower bound for this very new lower bound for p equals 3, that was found using artificial intelligence techniques, but as far as I know, it's still constructive. They just used sort of artificial intelligence techniques to find a good construction as far as I know. But I don't actually know what the size of the construction is, so it may be not humanly checkable anymore because maybe it's so big. I'm not quite sure. So this is a very recent paper and don't actually know all the details. But certainly the for p at least 5 is humanly checkable. It's just a specific list of 96 vectors. Okay, so what is special about p equals 3 here? Well, so in the case p equals 3, we can reformulate the question as asking about the maximum size of a subset of 3 to the n So I guess this question asks about the maximum size of a subset A of S3 to the n without three distinct vectors x, y, z, so that x plus y plus z equals 0. But we can reformulate that equation x plus y plus z equals 0, we can reformulate that to x minus 2y plus z equals 0, because in characteristic 3, that's the same thing. And so then you see that's the equation for a three-term arithmetic progression. So in characteristic 3, this problem up here is equivalent to the problem of finding the maximum size of a subset of f3 to the n without a three-term arithmetic progression. So in other words, for p equals 3, determining this Erdős-Ginzburg Ziff constant is actually a plain equivalent to determining the maximum size of a subset of f3 to the n without a three-term arithmetic progression. So that means without distinct vectors x, y, z, with x minus 2y plus z equals 0. And so this problem, asking about the maximum size of a three-term progression-free subset of f3 to the n, is actually a very famous problem called the CAPSET problem. And so more generally, just to give some context, more generally studying the maximum size of progression-free subsets of fp to the n or of the numbers from 1 to n is a very fundamental problem in additive combinatorics. One might say it's their most famous, or at least one of the most famous problems in additive combinatorics. And so a landmark result in this area is Semeredi's theorem from 1975, where he showed that for any fixed progression length k, so up here k would be 3, but he showed this for any fixed progression length k, the maximum size of a subset of the numbers from 1 to n without a k-term arithmetic progression is much smaller than n. So it's of the form little o of n. So the fraction of that maximum subset size divided by n goes to 0. So that was actually the main result described in Semeredi's Abel Prize citation. So this was really a fundamental result that had a huge impact, not just on additive combinatorics. Okay, so still not everything is understood here. In particular, the behavior of this little o of n term in this result is still not understood despite a lot of attention. So for k equals 3, in a recent revolutionary breakthrough of Kelly and Meka last year, the behavior of the quantitative behavior of this term is now much better understood, but for k at least 4, it's still widely open what shape that term actually takes. Okay, but that's more tangent to what we're talking about here. So we are talking about, I guess, the Erdős-Ginzburg Ziff problem. We just saw that for p equals 3, it's equivalent to the CAPSET problem. So here's again the CAPSET problem, asking about the maximum size of a subset of f3 to the n without a three-term arithmetic progression. And so here are some upper bounds that are known for this. A trivial upper bound is clearly 3 to the n, right? That's the size of the total space f3 to the n. With the pigeonhole principle, you can get roughly half that. So you can show that you can give as an exercise to your students. Then you can show an upper bound of roughly a half times 3 to the n with the pigeonhole principle. Meshulam improved this, showing an upper bound of a constant times 3 to the n divided by n. So that is, if you compare it with the total size of the space 3 to the n, it's sort of vanishingly small compared to 3 to the n. But on the other hand, it's just 3 to the n divided by a polynomial function n. Bateman and Katz improved this a little bit, showing that the size is at most a constant times 3 to the n divided by n to the 1 plus epsilon for some small constant epsilon bigger than 0. So they improved the exponent of this polynomial n here from 1 to 1 plus a little bit. And still this was considered a huge breakthrough published in the Journal of the AMS. But then a much, much bigger breakthrough happened in 2017 when Ellenberg and Reisweit proved a bound which is much, much better, which is namely exponentially smaller than 3 to the n. So for these bounds, you can see that it's 3 to the n divided by something that grows polynomially with n. And they showed that, in fact, the answer is 3 to the n divided by something exponential in n, and is therefore in spirit closer to the lower bounds. So Ellenberg and Reisweit showed that if A is a subset of f3 to the n not containing a three-term arithmetic progression, then the size of A is at most 2.756 to the n. And so if you remember from the previous slide, the best lower bound for this problem is roughly 2.2202 to the n. So there's, of course, still a gap, but it has the same sort of shape. So it's a constant strictly less than 3 to the n. Yeah. Okay, so yeah, so that means now So here's again the result of Ellenberg. So Ellenberg and Reisweit's result on the last slide I phrased it just for P equals 3, but in fact they proved something more general. So they proved a more general result for Fp to the n for any fixed prime P at least 3, again for the problem of not containing a 3-term arithmetic progression. So they showed that for any fixed prime P at least 3, if A is a subset of Fp to the n without a 3-term arithmetic progression, then the size of A is at most gamma p to the n for some constant gamma p only depending on p and strictly less than p. So strictly less than p is important here because clearly the size of A is at most p to the n if it's a subset of fp to the n. But the point is to have a bound that's exponentially better than p to the n by having a constant gamma p here which is strictly less than p. Okay, so just for the sake of completeness, the proof also gives a value for this gamma p, which is given by this term. So it looks a little bit complicated. Don't worry about what this term is. What's interesting to know, though, is that this gamma p is between 0.84 p and 0.92 p. So you can think of this gamma p to be, I don't know, roughly 0.85 p or roughly 0.9 p. Okay. So for p equals 3, if you plug in p equals 3 into this formula, the gamma 3 you get is exactly this 2.756 we saw on the last slide. So they showed that in the case of, so that was the result we saw on the last slide, that in F3 to the n, a 3-term progression-free subset has size at most 2.756 to the n. So it's not known whether this constant gamma p is tight. So it's not known whether that's the best possible, this value here, they got whether that's tight for this result. The best known general lower bound is roughly 0.54 p. So that's quite a bit less than this 0.85 p here. And that's a recent result of myself together with Christian Elsholz, Zach Hunter, and Laura Proske. But what is known is that this constant gamma p is tight for a certain multicolored generalization of this result. So it's a bit technical, so I won't state what exactly this multicolored version is. But there is some relatively natural multicolored version of this theorem. So there are basically three sets with 3 different colors. And so then you're looking for 3-term progressions across, basically. And so for this somewhat technical to state multicolored generalization, you get the same upper bound with basically the same proof. But in that multicolored generalization, that bound is optimal with this value of gamma p. And so that tightness is due to Kleinberg, Sauermann, and Speyer, relying on a result proved independently by Noreen and Peabody that was conjectured in the first version of their paper. So here back to the case of F3 to the n. So here, for simplicity, here's again the result stated in F3 to the n. And so this proof of Ellenberg and Reisweit used a new polynomial method, which was introduced by Kotleff and Pach only a few weeks earlier. And then a few weeks after the paper of Ellenberg and Reisweit came out, Tau introduced a reformulation of this method, which is now called the slice-rank polynomial method. And as the name suggests, this is another polynomial method. So in that new polynomial method is distinct from the sort of polynomial methods we talked about earlier with the combinatorial Nullstellensatz and also the other known polynomial. So there's various different polynomial techniques, but that was a distinctly new polynomial technique that was introduced in this sequence of works. And so, so with the slice-rank polynomial method, one can then, Tau gave this proof, reproved the theorem of Ellenberg and Reisweit in his new language with the slice-rank polynomial method. And so then one gets this bound. And as we already saw earlier, that now implies a bound for this Erdős Ginzburg Ziff constant in the case m equals p equals 3. So in the case of finding 3 points, one gets this upper bound. And so again, as we said, this proof relies on an algebraic technique, namely this new slice-rank polynomial method. So it's again an algebraic technique using polynomials, but in a very different way. So it's a very different polynomial techniques than the results of for S of fp to the n for small dimension n that we talked about earlier. Okay, so here's again a recap. So we we saw that for fixed p at least 3, determining this Erdős Ginzburg Sieve constant S of fp to the n is essentially equivalent to the following problem. So it's equivalent up to constant factors depending on p. And the problem was, what is the maximum size of a subset of fp to the n without p distinct elements summing to 0? And as we just saw for p equals 3, this was equivalent to the CAP-set problem. And so by the result of Ellenberg and Reisweit, one has an upper bound of 2.756 to the n for this problem here for p equals 3. So it's therefore natural to wonder whether one can also apply these new techniques and this new slice rank polynomial method to this problem for p at least 5. So we saw earlier result also for larger p of Ellenberg and Reisweit, but that was for 3-term progression free sets. And 3-term progression free sets is not the same thing as this problem except when p equals 3. But now, even though these are distinct problems, it's of course natural to wonder, could the technique also be useful for this problem? However, unfortunately, it doesn't work. So the problem is that the slice rank polynomial method relies on a new notion of tensor rank, the so-called slice rank. So in this technique, one considers certain tensors. And so the problem here is that the natural tensor associated with this problem here is not a diagonal tensor, and therefore one doesn't have a good lower bound for the slice rank. So for these results for 3-term progression free sets, one writes down a certain tensor, which is a diagonal tensor, therefore has full slice rank, just like diagonal matrices with non-zero elements on the diagonal have full rank. And so then one gets an upper bound on the slice rank via the polynomial expression defining it. And so that upper bound is still possible here, but the lower bound for the slice rank fails because the tensor isn't diagonal. And so one has no control over lower bounding the slice rank. So basically, the argument fails because the tensor is not diagonal. And so that the fact that the tensor is not diagonal is due to this distinctness condition here. So to illustrate this, let me sort of illustrate this again, maybe more clearly on the following slide. So here's the problem we are wondering about. And so, in other words, we are asking for the maximum size of a subset A of fp to the n with no solution to this equation where x1 to xp are distinct vectors in A. If we now, and so the point is exactly this distinctness here. If we weaken this a bit, we ask the following. So we're asking for the maximum size of a subset of A of fp to the n with no solution to the same equation where x1 to xp are not all equal. So that means we are excluding more solutions now, right? We weakened the condition for the solution, so that means we're excluding more solutions now. We're excluding now all solutions to this equation where x1 to xp are not all equal. Then, with a stronger exclusion, the slice rank polynomial method applies beautifully. One has a diagonal tensor, it applies beautifully, and one gets a very nice upper bound showing that for this bottom problem, the size of A is at most 4 to the n. So that's a straightforward application of the slice rank polynomial method. But this argument breaks down for the problem at the top that we actually care about because we don't have a diagonal tensor anymore because of this distinctness. So that 4 does not depend on p. So in fact, you get some number which is slightly less than 4 and depends on p. So you get 4 minus a little bit, where the little bit depends on p. But 4 means the statement as written is true independent of p. And so that's why I'm saying that's really a wonderfully good bound. You get an absolute constant to the n, where the absolute constant is independent on p. So it's a great bound. But it fails for at least the argument fails for the top problem. And we'll get back to this at the end. Okay, so let me now tell you what is known about this problem for a fixed p at least 5. So as we already saw, for p equals 2, it's trivial, and for p equals 3, it's a CAP-set problem. And so then the slice rank polynomial method applies. So let me tell you what's known for p at least 5, fixed p at least 5 and large n. So here's again the problem we care about. And so clearly, a trivial upper bound is the maximum size of such a subset can be at most p to the n. And so now again, you can ask, well, is it actually exponentially smaller than p to the n? And the answer is yes. So that was proved by Naslund a few years ago. So he proved that the size of A must be exponentially smaller than p to the n. In fact, he proved a bound written here. where this gamma p is again a constant strictly less than p, and it's actually the same constant as in the Ellenberg-Kreisweit bound for three-term progression-free subsets of fp to the n. So again, this gamma p you can think of as roughly 0.85p or 0.9p. Okay, so that means Nathorn proved a bound that such as set A with this condition here is at most roughly 0.9p to the n. So that means it's exponentially smaller than p to the n, but the base gamma p is still linear in p. So you might wonder, can you do better? Because, I mean, in the lower bound, there was the absolute constant 2.13 to the n. So a few years ago, I improved this bound, showing an upper bound, which is now of the form something to the n, where this base is now on the order of square root p. So I proved that if A is a subset of fp to the n without p distinct elements summing to 0, then the size of the set A is at most roughly 2 square root p to the n. And so this proof combines the slice rank polynomial method with combinatorial ideas in order to overcome this problem that the tensor is not diagonal. So it again uses algebraic techniques, namely the new slice rank polynomial method introduced by Tao, building upon the work of Kotlef-Fach and Ellenberg-Kreisweit. But this alone doesn't work, and so these additional combinatorial ideas go into this result. And so again, similarly to the Ellenberg-Kreisweit result for three-term progression-free sets, the same proof also gives a multicolored generalization of this theorem. So again, that's technical to state, and so I will spare you the statement, but the same proof gives a multicolored generalization with essentially the same bound. But interestingly, again, in this multicolored generalization, the bound is close to tight. So for this multicolored version, there is a lower bound of square root p to the n. So it's not exactly the same, but again, the behavior of the space is the same. It's on order square root p. And so that's very similar to the situation for the CAP-set problem, or more generally for the problem for three-term progression-free subsets in fp to the n, where the bound is known to be tight for the multicolored generalization, but not known to be tight for the original problem itself. And so one barrier for improving this result at the top here, and similarly for the CAP-set problem, is that in order to improve the result, an approach is needed which does not generalize to the multicolored setting. And so the problem is that most of these slice rank arguments naturally do generalize to the multicolored setting, and so therefore they cannot give a bound which is tight or close to tight in the multicolored setting. They cannot improve upon a bound that's already tight in the multicolored setting. So in fairly recent work, we overcame this barrier for this Erdős-Ginzburg-Siff problem setting here for p-distinct vectors summing to 0. So in joint work with Dmitry Zakharov, who is a graduate student at MIT, we improved the bound for this problem here as follows. So we showed, so this looks a little bit technical, but we showed that for any subset A of fp to the n without p-distinct vector summing to 0 can be upper bounded by a term of this form for every fixed epsilon bigger than 0. So you can choose your favorite epsilon, for example, 0.01, and then you get a bound of this form where d epsilon p depends on epsilon p and c epsilon depends on epsilon. Okay, so the proof combines the slice rank polynomial method with combinatorial and probabilistic arguments, as well as an ingredient from additive combinatorics, namely the higher uniformity version of the Balog-Semeridi-Gauss theorem. And this higher uniformity version is due to Borenstein and Crude. Okay, so again, we take this polynomial method, the slice rank polynomial method, and combine it with additional things in order to overcome this problem of the tensor not being diagonal. And so as a corollary, as we already said, this problem about not having p-distinct elements summing to 0 is essentially equivalent up to constant factors when p up to factors only depending on p to the Erdős-Ginzburg-Siff problem. And so as a direct corollary, one gets that for every fixed epsilon bigger than 0, for all primes p and all n, one gets this bound for the Erdős-Ginzburg-Siff constant. So to make that a little bit more concrete, because it's annoying to have all these variables, and it's already the 4th day of the conference, and everyone's a bit sleepy. So the upshot is we get this bound for s of fp to the n, which is a constant depending on p, times something exponential in n, where the thing exponential in n is on the order of p to the 0.01. And if you don't like p to 0.01, you can take any other number epsilon there. So that's the bound. without written so many quantifiers. So take your favorite number. I took 0.01. Then you can write an absolute constant times p to the 0.01. So the absolute constant only depends on your chosen value of 0.01. And then that's your exponential base. And then there's a prefactor depending on p. So okay, so that's our bound for the Erdős-Ginzburg-Ziff constant in the range where p at least 5 is fixed and n is large. Okay, so here's again the corollary, this time written in the slightly more annoying variable version. So let me get back to the question of the lower bound. So the best lower bound for this Erdős-Ginzburg-Ziff constant for fixed p and large n, for fixed p at least 5 and large n, as we saw earlier, roughly 2.1398 to the n. That's due to Adele from 2008. And so that means there's still a significant gap between this upper bound and this lower bound. Because in this upper bound, if you think of here the base as roughly on the order of p to the 0.01, but it still grows with p, whereas in this lower bound, it's an absolute constant. And that also gets back at, I forgot whose, your question earlier with this, in the slide where we contrasted the distinct with the not all equal, we got this absolute constant 4 to the n as a bound. And so here the lower bound is also an absolute constant, and it's completely conceivable that the true answer is actually an absolute constant, but that's open. So it's an open problem to determine whether there is an upper bound of the form a prefactor depending on p, only on p, times an absolute constant to the n. So there's always it's clear that the prefactor depending on p is needed, but the question is, should the exponential base to the exponent n be an absolute constant, like in this lower bound here, or should it be something depending on p, like here? Like this grows very slowly with p, like p to the epsilon for any epsilon you want, but it still grows with p. And so the big open problem is, can you actually put an absolute constant there? And I could see the answer going either way, I'm not sure, but I think it's very interesting to try to figure out what's going on here and whether it's a constant or not. And yeah, so one more remark about this. So in the opposite parameter regime, where n is fixed and p is large with respect to n, so that was sort of the regime we talked about earlier, in the talk, Zakharov proved the bound which has this shape. So in this regime, he proved that S of fp to the n is at most p times 4 to the n. However, his methods don't apply in the regime where p is fixed and n is large. So basically, in the opposite regime, you have such a bound, but the question is, do you also have such a bound when p is fixed and n is large? So that's all I wanted to say about Erdős-Ginzburg-Ziff constants, but because I have 2 minutes left, I want to make some more advertisement of the journal Combinatorial Theory. So we already saw at the end of the last talk when the Combinatorics Consortium presented, there was a presentation about the Combinatorics Consortium, and you saw the logos of 2 different journals, and so Combinatorial Theory is one of them. And so that's a mathematician-run journal which is owned by its editorial board. So it was created by flipping the Elsevier-owned Journal of Combinatorial Theory Series A in 2020. So that's relatively recent. It's diamond open access with no fees for authors or readers. And so since it's relatively recent, not all of you may be aware of it, and so that's why I'm advertising here a little bit. Okay, here's a bit more technical information. So the first volume was published in 2021. You can read the rest yourself. Just to advertise a bit more, the scope is sort of all around combinatorics, so additive, algebraic, analytic, enumerative, extreme geometric, topological, and probabilistic combinatorics, as well as theoretical aspects of their applications to other areas of mathematics and the sciences. So I think most people in this room find themselves somewhere within the scope of this journal, and we are always looking for, so I'm speaking here on behalf of, I'm one of the editors, and so I'm speaking here on behalf of the editorial board. We're always looking for strong submissions, so that's why I wanted to advertise this here. Thank you.
Much for this wonderful talk. Are there any questions?
and then you have this kind of like absolute constant, right?
Yeah.
To the n as the bound.
Yeah.
And the case that you really cared about with the centroids was when none of them are allowed to be equal.
Yeah.
But you could, in theory, look at something in between where you say you don't have like 3 of them that are equal, or you allow, you know, have you thought about whether that changes sort of the qualitative behavior of the...
Yeah, so that's an interesting question. Actually, as one of the ingredients going into this result here, we proved something on the form, okay, I hope I remember it correctly, but something on the form of if you only want 10% of them to be equal, where you can obviously replace 10% by whatever fraction you want. So for any fixed fraction, let's say 10%, if you forbid a solution, if you forbid all solutions where 10% of them are equal, then you get, again, an absolute constant, where the absolute constant depends on your chosen value of 10%. But so that's now, I guess, one way to ask the question. So then I think we have a reasonably good bound. If you ask the question of the form, like, not a constant number to be equal, I don't know off the top of my head, but I would assume that that's probably similar in difficulty to all of them distinct. But I would have to think about it.
I have, if you fix some p, say 7 or 11, you can certainly choose a range of epsilon. Have you checked to see what sorts of values inside the exponential you get for this c epsilon p to the epsilon? And is there some nice value of epsilon for relatively small p, or is this 0.01 sort of a signifier that you always want to choose the smallest epsilon?
So, okay, so this bound is sort of meant to be interesting if p is relatively large, so not 7 or 11. I think if you, so I don't know, I don't remember whether in our paper we actually give an explicit value for the c epsilon, but my guess would be if you sort of plug into this proof 7 or 11, you get something worse than the trivial bound here. If you, as far as I know, for 7 or 11, the best upper bound is this bound. So I guess here you have 2 square root p, so that's something very explicit, and you can plug in 7 or 11, and you get something that's better than the trivial bound, and as far as I know, I think it's also the best bound in those cases. And this bound really only becomes good if p is reasonably large.
More questions?
And yeah, so one more thing, the 0.01 had no particular significance. That was just because everyone might be tired and not want to read too many quantifiers.
Okay, yes, Valentin.
Is there some literature about the same kind of question in non-commutative group, like this group?
So did you say in commutative or non-commutative? Yes, so I think these types of questions are also studied in non-commutative groups. Then you have to be, of course, a little bit careful what exactly you mean. There is actually quite a bit of literature on that, and I think they've sort of settled on a definition they mostly use. I guess there's different ways to ask a question, but mostly they ask about basically the multiset setting, and you can choose the factors that you want to choose in whatever order you want, so you're allowed to permute. Yes, so there are some things known, but as you might imagine, a lot of things are unknown, because even for simple groups like fp to the n, it's unknown. But for some small groups, like I guess for groups up to a certain small size, something like 30 or something, some of the things have been calculated with computer aid. And, yeah.
Thank you.
So going back to your original question where, I mean, the prime p is still an arbitrary integer n, or m, then if I fix the dimension n, is the function increasing when m grows? I mean, m is an arbitrary integer.
So I'm not sure I heard correctly. So you fix m and let n grow.
No, I fixed the dimension n.
You fix the dimension n and let m grow.
Yeah.
And your question is it even clear it's increasing in m?
Yeah.
Yeah, so I don't think it's a priori clear that it's strictly increasing. If you increase by m by 1, it's not sort of clear that but it's clear that it's sort of eventually increasing. So if you double m, it's at least as big as it was before doubling it.
Okay, so there. Okay, so there is indeed an example where the function is not increasing.
So I don't think there's an example. I'm just saying I don't think. So I'm not sure whether anyone has sort of ever tried to prove this. I'm not aware of a result stating that it's strictly increasing. So I guess part of, well, maybe you might find it weird why has nobody tried to prove that. I think part of the philosophy here is that most people try to understand the growth behavior of the function, getting an upper bound and a lower bound, which are sort of hopefully close in spirit. And so how exactly it oscillates between them would be sort of the next order question people would try to understand after they understood the overall behavior. So that's why I think nobody has really, as far as I know, tried to prove that it's strictly increasing. I'm not aware of any examples showing that it's not. In fact, I would be very surprised if it's not strictly increasing. But I'm also not aware of anyone showing this, and it's certainly not obvious. Yeah.
Thank you for your answer.
More questions? Okay. So let's thank the speaker again.